Hello friends, in this video I'd like to solve the following problem from the Slovenian International Mathematical Olympiad Team Selection Test 2005, problem number 3. We wish to find all positive integers m and n such that m squared minus 4n and n squared minus 4m are both perfect squares. So here are my hints for this number theoretic problem. First, without loss of generality, you may assume, because of symmetry, that m is less than or equal n, and first try to show that m must be greater than or equal 4, and check first case when m equals n, and then case when m is strictly less than n, and finally, most crucially, try to squeeze n squared minus 4 times m between some two squares. And that should be enough to eliminate most of the possibilities. So give this problem a try and I will see you in just a minute. Okay, so as I suggested, we may assume because of symmetry that m is less than or equal n. Very well. And now notice the following. M squared minus 4 times n should be a perfect square, so definitely it should be greater than or equal 0. But at the same time, notice that it's less than or equal m squared minus 4 times m, because here we are subtracting bigger number than there. And that is m times m minus 4, so definitely m must be greater than or equal 4. Because here we have a positive number, so this number must be non-negative, so it must be greater than or equal 4. Now I wish to consider two cases. Case number 1, when actually m equals n. m equals n. What then? Then notice that m squared minus 4 times n and n squared minus 4 times m are the same, and they are both equal m squared minus 4 times m, and we can do a classic trick, plus 4 minus 4, and that can be written, as m minus 2 squared minus 4. And remember that that should be a perfect square. So we have some perfect square equals some other perfect square minus 4. But let's write first perfect squares. The perfect squares are 0, 1, 4, 9, 16, 25, and so on. And what two perfect squares differ by 4? Well, the only two perfect squares which differ by 4 is 0 and 4. 0 and 4. So that means that m minus 2 squared must be equal 4. Yes? So here we have 4, and here we have actually 0. Okay, when does it happen? Well, i.e. that happens when m equals n equals 4. So now we have one pair of solutions. M equals n equals 4. Very well. Let's move on to our second case, case number 2. Case number 2, where m is strictly less than n. Notice that then definitely n is greater than 5 or equal 5. Why is that? Well, because m is greater than or equal 4 and n is greater than m. So it's 5 or more. And moreover, it's the crucial step. Notice that we have the following two estimations. N squared minus 4m is definitely less than n squared, because here we're subtracting some number. But also, notice that this number is greater than n squared minus 4 times n. Why? Well, because we are subtracting bigger number than there. Very well. And also, I claim that this number is strictly greater than n minus 3 squared. I claim this. How to justify it? Well, notice that this inequality is equivalent to saying that n minus 3 squared is less than n squared minus 4 times n, which in turn is equivalent to saying that, that 9 is less than 2 times n, so 4.5 is less than n, which is true because n is greater than or equal 5. It is true because n is actually greater than or equal 5. Now, by now we have demonstrated that this number, which is supposedly a perfect square, is somewhere between n squared and n minus 3 squared. But what squares are between these two numbers? Well, there are only two possibilities. So by this and by that, by asterisk and double asterisk, by asterisk and double asterisk, we have only two possibilities. Namely, n squared minus 4 times n m equals either n minus 1 squared or n squared minus 4 times m equals n minus 2 squared. These are the only squares strictly between these two squares. Yes? This is what I mean by squeezing some number between two squares. That eliminates most of the possibilities. And let's consider these cases separately. So let's consider them separately. Maybe I will mark this condition triangle, and this I will mark square. So, oh, maybe not, you know what, no. Let's consider two cases, it may be clearer. Case number 1, n squared minus 4 times m equals n minus 1 squared. Let's expand it. N squared minus 4 times m equals n squared minus 2 times n plus 1. In other words, 2n minus 4m equals 1, which is clearly impossible because this number is even and this number is odd. Impossible. Impossible. No solution there. Case number 2. N squared minus 4 times m equals actually n minus 2 squared. Let's expand it. N squared minus 4 times m equals n squared minus 4 times n plus 4, which means that n equals m plus 1. N equals m plus 1. Okay. So maybe let's write it explicitly that n squared minus 4m is a perfect square if and only if n equals m plus 1, provided that n is strictly greater than m. Okay. Now, let's use our second condition. Not only n squared minus 4m is a perfect square, but also m squared minus 4n should be a perfect square. So let's write m squared minus 4 times n, and let's expand it, m squared minus 4, and now instead of n, let's put m plus 1. So it's m squared minus 4m, and we have minus 4, but minus 4 can be written as plus 4 minus 8. And that is m minus 2 squared minus 8. Okay, so remember that this is supposedly a perfect square. This is supposedly a perfect square. And here we have another perfect square, minus 8. So let's write once again our sequence of perfect squares. And which two perfect squares differ by 8? Well, there is only one possibility, namely 1 and 9. There are the only two perfect squares which differ by 8, because the further we go, the bigger the difference is between two perfect squares. So it must be the case that this is 9. So let's write it. So m minus 2 must be actually equal 3, m equals 5, and so n equals 6. Okay, and that's the only possibility, 5 and 6. So now let's combine everything together. All our solutions. Well, we have 4, 4. We have 5, 6. But remember that that's all when m is less than or equal n. We can have it the other way around. So we have actually only 3 pairs of solutions. So solutions. So we have exactly 3 pairs of solutions. Namely 4, 4, 5, 6, and 6, 5. And that closes our problem. So as you have seen, classical trick, squeezing some supposed perfect square between two squares which are not too far apart. Yes, because notice that I have squeezed this number between n squared and n minus 3 squared, and these two squares are not that far apart. So we have only finitely many possibilities, and we have verified them case by case. So yes, very nice problem from Slovenia. Thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.